Hello friends, in this video I am going to discuss about the questions that have come in CSIR-UGC net, okay, from 2012 to 2019 for the chemical science. So here I am going to discuss nearly 13 questions which I have already prepared. So what I will do is I will solve these questions, okay. Then I have written already the questions in this paper. I will solve that questions and I will give the answers also, okay. So first question we can see that it is asked which of the following transitions require the least energy. So we can see that option is given from n to pi star, then from pi to pi star, and from sigma to sigma star, n to pi star. So how to solve this question? If we see the energy level, then this is sigma, this is pi, this is n, this is pi star, and this is sigma star, okay. Star means what? Anti-bonding. So question means what? Which will require the least energy. So whose transition will require least energy among these four options. So if you see n to pi star, that means from this n to this pi star transition, this one. And from pi to pi star means from this pi to this pi star, this transition. And from sigma to sigma star, which require very high amount of energy. And from n to pi sigma star, from n to sigma star. So we can see that pi to pi star requires highest amount of energy, but here the question is asked which of the following transition require the least energy. So if we see the least energy, then we can see from n to pi star, this transition requires least energy. So the correct option will be this A. The next question is which of the following does not have a presence in NMR? NMR means nuclear magnetic resonance, and in NMR what happens, any atom, if they want to show nuclear magnetic resonance, they have to satisfy some conditions, okay, regarding their nuclear spin, because this nuclear magnetic resonance is based on the nuclear spin. So here it is asked that which of the following does not have a presence in NMR. So for this one we have to understand one thing, that is if there is one law in the NMR, okay, if both the proton and neutron of the atom are even, if both the proton and neutron of the atom are even, in that case what happens, the molecule will have, the atom will have its nuclear magnetic spin is equal to 0, okay. But if one, that means proton is odd and neutron is also odd, then in that case we will see that I will be equal to integral multiple, okay, or like 1 2 3 like this. But in this case, if this I is equal to 0, then what will happen? If this I is equal to 0, that means the nuclear spin is equal to 0, that atom will not show the NMR spectra, okay. So if we see, then fluorine is already, we know that the atomic number of fluorine is 9, no, and this is also 19, that means atomic mass is 19, so both are odd. Same way hydrogen, one is odd and another is even. But if we see about this carbon 12, okay, this one carbon atomic number is 6, and similarly here it is isotope of carbon 12. Okay, there are many isotopes, carbon 13, carbon 14 is also there, but for this isotope, particularly for C12, what happens, its atomic number is 6 and its mass is also 12. That means both are even. If both are even, that means I is equal to 0, its nuclear spin will be 0, nuclear spin quantum number, this I means nuclear spin quantum number, they both will be 0, and in that case this atom will not show any NMR spectra. Okay, so the answer will be this C number. Next question is this one. This is the molecule. How the question is, this molecule shows dash number of NMR signal or signals. Now how to identify that which molecule will show how much signal, NMR signal? So for that we have to understand about the chemical environment. Okay, if you require that, then I can make video on the spectroscopy also, but particularly now since this is what we are solving now, so I'm going to directly use those concept here. So in case of NMR signals, if you want to identify the number of NMR signals produced by the compound, then what we are going to see, we will see the chemical environment. Okay, so this is a compound given here, which can be, which I will write here. Okay, CS3. So if we see, then this CS3, this CS3 and this CS3, all these methyl group, they are in the same they all these three methyl groups, they are in the same environment. How we can say that they are in the same environment? Because you can see here that these methyl groups, say suppose this is 1, this is 2, this is 3, so this methyl group is here you can see 1, 2, 3 is away from this methyl group by 3 carbons. Similarly, this methyl group is separated to this methyl group by 3 carbons, and this methyl group also by 3 carbons. It is separated, and this methyl group from here, it is separated by 3 carbons. Similarly, this methyl group separated by 3 carbons from this methyl group. So they are in the same environment. These 3 methyl group, they are in the same environment. If all these 3 methyl group, they are in the same environment, then they are going to give single same signal. Okay, they are going to give the single same signal. Again, we can see this compound is not a, I mean this aromatic, this is not an aromatic compound. Okay, this is a cyclohexane. Then here there is hydrogen, and this carbon also have hydrogen. And here we have hydrogen. So to this carbon atom to which the methyl group is attached, hydrogen is also attached. Okay, that means here is also hydrogen, and here we have hydrogen, and here also we have hydrogen. So all these 3 hydrogens will show they are in the same similar environment like this methyl. Okay, so so they will also show the same single same signal, they will give the single same signal. And similarly for these 2 hydrogen, they are also in the same environment. If we see, okay, this hydrogen and this hydrogen to which methyl group is not attached, this hydrogen, wait, let me write it in this way. So here we have 2 hydrogen. So each of this carbon will have two hydrogen. Okay, so this hydrogen will also give only one signal. They will give the same signal. Why? Because this hydrogen is separated from this hydrogen by how much carbon? One carbon. Okay, and similarly this is the distance is same, no? So they are in the same chemical environment, so they all these three hydrogen will give single same signal. And similarly the hydrogen which is attached to the methyl group, here will be hydrogen, here will be hydrogen, here will be hydrogen, which are attached to the methyl group. They will also give the single same signal. And similarly this methyl group is giving another single same signal. So together if we see, then there is three signal, one from all these three methyl group, second one from the hydrogen attached to this carbon atom to which the methyl group is attached. They will all these three hydrogens will give single signal, and the hydrogens which are not attached to the carbon atom to which this methyl group is attached. Okay, so all these will also give single signal. So total three signal will be there. In option we have 1, 2, 3 and 4, no? So this will be 3 only. So the next is the major product obtained in the following reactions. So here the reactant is given this one, and these are the things. Methyl iodide is there, and silver oxide, water, and heat. So what will be the product? So this product we have to find, and this is from the organic part. Okay, and whenever we say about organic part, it means we have to find them with mechanism. Without mechanism it will not work. So let us see its mechanism. What will be its mechanism? You see here, that's this is the, in this case is the nitrogen have lone pair of electrons. So this nitrogen will take this methyl group, methyl iodide, and it will become Me3. This methyl will become Me3 here, then here iodine, no, negative, and this nitrogen becomes here positive, and this will remain as it is. CS3 means what? Methyl, so I'm giving just Me. Okay, now nitrogen will take this bond. So CS3, no, so this will become positive. Okay, this will become positive. So we have, in the presence of this one, silver oxide and water. Water means we have OH negative. So this OH negative will attack this electrophile, I mean this carbocation. This will be in this way. So now what we are going to see is, if we heat this one, because their heat is also there, if we heat this molecule, then what we will see, the water will be released. Okay, after releasing water it becomes like, and this will become phenyl, and this is, and as soon as this hydrogen is eliminated along with this OH by as a water, this bond will come here. Okay, so it will become double bond, and we have here hydrogen. So this will be the answer. So in this option we have, so this is our answer. Okay, so you can see here that this first one, this molecule can be written as CS3 pH and hydrogen. Okay, so this is the first option is like same. Okay, now so this will be the product. A will be the answer for this. Then next we have question number 5. In the question number 5, again similar reaction, organic reaction is given. The major product obtained in the following reaction. What will be the major product obtained in the following reaction? So this is a compound, and here we can see it is treated with acid. So what will be the product? Similar mechanism we have to do. We can do with same mechanism. Okay. So first we will draw the product, I mean the reactant. So this is our reactant. Okay, by treating with acid, that means what will happen? We know this is a oxygen. Oxygen means there are lone pair of electrons. So this will take, since oxygen will be nucleophile, it will attack on this proton. Okay, after attacking this one, it will itself become unstable. Then what we are going to see, OH2 positive we will get. Then it will take away this bond and it becomes this. Here hydrogen will be there, no, still there will be one hydrogen by this carbon. It is hydrogen will be there, and this carbon becomes positive here. Now what happens, this phenyl will migrate at this position. So now what we will see, this becomes positive here. Okay, and phenyl will come here. So as soon as hydrogen is eliminated, this bond will make a double bond. Okay, it will make a double bond. Then we are going to see this type of product. So in the answer we have this one, no, oh sorry, this metal. Okay, this C number, if we see, our product is similar to this C number, no. So the correct answer for this question number 5 will be C number. Okay, and this is the mechanism for this. The next question is this one. For tetrahedral complexes which always exhibit high spin states, the maximum CFSE means crystal field splitting stabilization energy. So what will be the, for the tetrahedral complexes which always exhibit high spin states, the maximum CFSE is, so it speaks about the high spin states. High spin state means, and it is a tetrahedral complex. So since it is a tetrahedral complex, then what we are going to see, okay, we require the concept of many things here to solve. Okay, Okay, this is our T2C and this is our EC. So for this is for a tetrahedral complex. So what happens? High spin complex means what? Highest number of, there is maximum number of unpaired electrons, and low spin complex means there is no any unpaired electrons. Okay, so for tetrahedral complex, this is the maximum number of unpaired electrons that can be attained in easy orbital. Okay, so this way. So how we were going to find a CFSE? CFSE can be simply written as this mass energy is minus 6 dq, and that is your 4 dq. Okay, but they together are 10 dq. Okay, or that is what we call the crystal field splitting, that is delta, not tetrahedral. No? Now what we are going to see is that there are 2 electrons. No, so 2 into minus 6, we have to multiply this way, and minus, there is no any electrons in the T2Z orbital, so we can write like 0 into this energy, we have to multiply here 4. This gives the, this is actually the formula for the CFSE. So that is equal to, we are going to get minus 12 minus, or this is your 0, no, so that is equal to minus 12 dq. So this will be the answer. So the question for for tetrahedral complexes which always exhibit high spin state, the maximum CFSE is minus 12 dq. Okay, this one. So next we have question number 7, that is the value of n. So the value of n for the following molecule according to Haeckel rule. So Haeckel rule is actually the rule that is used to find out whether the compound is aromatic or it is anti-aromatic or non-aromatic. Okay, so if we consider, so it is what, this compound is called pyrene. Okay, and this is a very special compound because in Haeckel rule what you are going to see is, for aromatic the compound should have 4n plus 2 pi electrons. Okay, this is the formula if the compound is aromatic. And in case of pyrene, this is a pyrene. Okay, then if we see, then we can see that 1 2 3 4 5 6 7, but 1 2 3 4 5 6 7 8, it should be 8. Okay, oh sorry, this will not be there. Okay, it will be here only. No, I'm sorry, it will be here 1 and here 1. Okay, this 2 will be the pi bond. So in case of pyrene, we will see 1 2 3 4 5 6 7 8, there are 8 pi, that means total 16 pi electron. Okay, but actually it is 14 pi electron. Okay, this is exceptional because this middle bond, the bond that is present in this middle of this compound will not be taken. That is why it becomes 14 pi electron. We will just take this outer 7 double bond. Okay, electrons of this 7 double bond, outer 7 double bond. So this is the outer surface. So we are going to take only this. We are not going to take this middle one because this middle one is not involved in delocalization. Okay, it cannot involve in delocalization. Only these outer electrons will involve in delocalization. So we are going to take total 14 pi electrons. So what happens, 4n plus 2 is equal to 14. This implies n is equal to how much, 12 by 4. that is equal to 3. So 3 will be the value of n. Okay, so the value of n we have to find, so the answer will be this C number. Okay, the next question is question number 8. So in question number 8, what it is giving is that using molecular orbital theory, MO theory, predict which of the following species has the shortest bond length. So if you want to know the bond length, you have to find out the bond order, because bond order is inversely proportional to bond length. Okay, so for this oxygen species, the bond order for O2 is nothing but it will be given by half of number of bonding electrons minus number of anti-bonding electrons. In O2, number of bonding electrons is 10 and number of anti-bonding electron is 6, because O2 means what? 8 plus 8, 16. So this is 16, no, 10 plus 6, 16. But out of this 16, 10 is bonding and 6 is anti-bonding. So it will give us 2. Okay, now the question is, it is O2 2 negative. Okay, O2 2 negative means what? We have to add 2 more electrons. Where? Here. Okay, if we add 2 more electrons here, then we are going to get 6, 7, 8. So 8 means what? 10 minus 8. So for O2, 10 minus 8 means it will be 2. So 2 by 2, 1. And for similarly O2 2 plus. 2 plus means we will have to remove 2 electrons from this 6. So if we remove 2 electrons, that means it will become 4. 10 minus 4, that is equal to 6. 6 by 2, that is 3. O2 2 positive will be 3. Similarly O2 positive means remove 1, it will become 5. 5 by 2, it will become 2.5. And for O2 negative, what happens? We will add 1 more electron. That means 10 minus 7, it will be 3. 3 by 2 is 1.5. Okay, so I told you that bond order is inversely proportional to bond length. Whose bond order is more, that bond length will be short. O2 2 positive, bond order is 3. If it is 3, that means highest. Okay, so if it is highest, that means it will have the shortest bond length. So here we have to find shortest bond length. So shortest bond length will be O2 positive, B number. Then the next question is, two functions are said to be orthogonal if integration of psi n into integration of psi n star dz has value 0, infinity, 1 and none of this. So what will be that? So if two functions are said to be orthogonal, integration psi star dx, that is equal to 1. If it is the condition, then that is called normalized. Okay, normalized wave function. Then what we will say, that psi is the normalized wave function. Then if it is psi star dx is equal to 0, then we call it orthogonal. At the same time, if both the condition is satisfied, if it is integration of psi star dx is both how much, it can be both 1 as well as 0, then we call it orthonormal. Okay, so this is the question from the quantum part of the chemistry. So that for orthogonal, it is said two functions are said to be orthogonal if orthogonal means 0, this should be 0. Okay, so the question, the answer will be A. The next question is, under the influence of air and light, chloroform decomposes into carbon tetrachloride, that means CCl4, phosphine, chloral hydrate, none of these. So what will be the answer? Okay, under the influence of air and light, chloroform decomposes into, chloroform means CsCl3. Okay, so under the presence of oxygen, that means air, and if we give light here, this is a very normal question. Okay, so what we are going to get, we will see that there will be this one, HCl. Okay, and this is what we call phosgene. Okay, which is a poisonous gas. Phosgene. Okay, answer will be the phosgene. Okay, and this will be the reaction of that in the presence of air, and then light. The chloroform will react to give phosgene, and it will release hydrochloric acid. So that is the 10 number question. Then the next question we are going to see, question number 11. Okay, question number 11 is, zinc is involved in functioning of oxytocin, antibodies, nucleic acids, and insulin. The correct answer is this one, insulin. Okay, another is, aspirin is what? Methyl salicylate, acetyl salicylic acid, phenyl salicylate, or phthalic acid. If we see the structure of aspirin, then structure of aspirin is like this. Okay, this will be this one. This is the structure of aspirin. Okay, and aspirin is a antipyretic drug. Okay, it reduces the pressure. That means if you have that one, pressure and all. Okay, if your body temperature is increased, then this antipyretic drug will reduce that. Okay, it will help in reducing the temperature of your body. So this is the structure of aspirin, which is an antipyretic drug. And question is what? Question is, aspirin is methyl salicylate, acetyl salicylic acid, phenyl salicylate, and phthalic acid. You can see here acetyl group. Okay, this is a acetyl group, and this is a carboxylic group. So it is what? This one, acetyl salicylic acid. Okay, that is the aspirin. The last question that I am going to discuss is question number 13. Okay, chemical shift is equal to, so this is given here. So chemical shift is usually given by, this is again from the spectroscopy part. This is the delta chemical shift, new sample, new TMS. TMS means tetramethylsilane. Okay, by operating frequency. Okay, in mega this one, mega cycle, you can say. What I have or what we learn is usually this one, new sample minus new TMS by new node. This is operating frequency into 10 to the power 6 parts per million. In the book you are going to see this formula. Okay, and this is operating frequency. So in mega cycle means what? This 10 to the power 6, it represents this one. Okay, so ultimately if we see, then the correct answer will be new sample, new reference. Reference means it can be anyone. Okay, but mostly we take this TMS, tetramethylsilane, whose structure is like this, tetramethylsilane. Okay, these are methyl. Okay, so that is the reference molecule that we take. Okay, to find out the chemical shift. So the answer is this A number. Answer is the A number. Okay, so these are the questions that I have discussed for our CSIR-UGC net. Okay, which has come in 2012 to 2019 for the chemical science. Okay, hope you like the video, friends. Thank you. If you like the video, then like and subscribe.